I am Mr. Ish. Thank you for joining me for this video. A chemistry video on a topic that is usually a bane for most students, high school students, acid-base titration. There can be 4 combinations of this acid-base titration. You can have strong acid, strong base, weak acid, strong base, strong acid, weak base, and weak acid and weak base. In this video, we're looking at the most common form because that form is the most practical in terms of biological and real-life applications, weak acid and a strong base. A weak acid can be something like acetic acid, or it could be carbonic acid. A strong base could be sodium hydroxide. You would be titrating that. Remember, when you're doing acid-base reactions, you're always going to have a fixed volume of a acid, and here the weak acid I'm going to symbolize in all instances as HA. You'll have a fixed volume of HA. You'll start out with 0 ml of the base which is added. The base, the strong base which we're adding, will start out with 0 ml, then we'll slowly add increments. The next one will be 12.5 ml, the next one will be 25 ml, then we'll have 37.5 ml, and in these increments we'll see how the pH changes. You know, when you're going to do the pH calculation, initially when you have 0 ml of base, you'll have a pH based solely on the acid concentration. Then as you start adding base, the pH changes, it starts going up, raising up, and then there'll be a point where the equivalence point is reached. You have to understand what the equivalence point is. The equivalence point is that point where the moles, let's just say HA, moles acid is equal to your moles base. That's exactly what you have, and I'm going to symbolize as OH minus. You want to start out all acid-base titrations by the calculation of your equivalence point, and trust me, it's not hard. Everything is always with regards to molarity of your acid in terms of the molarity of your base at the equivalence point, or you can say moles is equal to moles of acid equal to moles of base. You know what moles is going to be. You know molarity is equal to moles divided by volume. So if you want to find the moles, you're doing M times V, the molarity times the volume, molarity times the volume, the molarity of your acid times its volume, the molarity of the base times its volume. That'll give you your moles, that'll give you your equivalence point too. Everything is seemingly hard, but trust me, the method that I'm going to show you is going to greatly simplify all of this. You should be comfortable with determining the pH change for a weak acid, strong base when there is no base. And then as you slowly start adding base, you should be able to do that pH determination. When you're doing acid-base titrations, you should always keep something like this in your mind. A titration curve where you have on the x-axis your volume of base added. On your y-axis you have your pH. Initially when you're starting out with 0 ml of base, your pH is dependent solely on the concentration of your acid. As you start adding base, the pH starts rising up, but it doesn't rise up too fast because the acid is able to buffer against that hydroxide ion concentration. But there comes an equivalence point. At the equivalence point, you have equal amount of this, equal amount of your acid. The only problem is the base is a very strong base, the acid is still a weak acid. You have a shoot up in the pH. The pH just shoots up. After that equivalence point, the pH is pretty much dependent only on the hydroxide ion concentration. The amount of hydrogen concentration has all been neutralized anyway, so everything is then dependent on the hydroxide. Initially everything depends on the hydrogen ion concentration. Here in this buffer area you have the equal interplay between hydrogen and hydroxide. Here at the equivalence point you start seeing the hydroxide ion starts overcoming the hydrogen ion. Over here it's pretty much basically the hydroxide ion concentration that's determining the pH. All of this will make more sense as we look at our example. We have one example, but that example will have 4 parts. Each part will be based on the volume of the base. 0 ml, 12.5, 25 and 37.5. I guarantee you this video is not going to be as hard as it seems. Once you see it the way I like to do it, you might find this specific topic not as hard as before. And now the fun begins. Our situation is this: we have 50 ml, 50 milliliters of 0.1 molar weak acid, which I'm symbolizing as HA. It could be formic acid, acetic acid, carbonic acid. We have 50 ml, 0.1 molar. We are going to titrate this against 0.2 molar sodium hydroxide. On the side over there, we have volume 0, 12.5, 25 and 37.5. We have to find the pH of this entire system as that amount of base is added, and then we'll start plugging in everything. Here we're looking at start with 0 ml. When you have a 0 ml of base, you have nothing in the system other than acid. You can do it exactly as I'll tell you, and I'm going to talk about shortcuts as we go along. Initially you have nothing but a weak acid in the presence of water. It will dissociate and it will well, let's just use the word ionize. It will dissociate and ionize to form a conjugate base and a conjugate acid. You have a certain amount and certain change and a certain final amount. What will I put over here? Normally you can put moles over here, but since you have nothing in the system other than acid, just put the molarity. You have a 0.1 initial amount of HA. You have 0 amount of conjugate base, 0 amount of conjugate acid, because everything has just started. Everything will change. This will obviously decrease. These will obviously increase with time. You'll have x. Here you'll have 0.1 minus x. For all instances and purposes, assume here the equilibrium constant of this weak acid, because you need it, is basically 3 times 10 to the minus 4, which is not a large number. Anytime you have a large number here, something which is larger than 1 or 0, you cannot make the assumptions I'm talking about here. The shortcuts we will take, you cannot do that. You can do those shortcuts very easily when these values here are small. What is that first shortcut you can take? You know you're going to do your Ka equation, your acid dissociation equation. It's going to be the conjugate base times the conjugate acid divided by your HA. In all instances, water is always liquid. Liquid and solids do not appear in this style of equation here. And I mean by solids, pure solids. Pure solids will not appear. This is what we have. You have to put their concentrations in. I have an x, I have an x, I have here 0.1 minus x. Your first shortcut and assumption is this. Because this value here is small, you can eliminate this minus x. Because if you don't, you'll end up getting into a quadratic formula type of situation and your work will become large and long and cumbersome. This shortcut is very acceptable for Ka values which are small. And all of this is equal to 3 times 10 to the minus 4. All you have to do is solve for that x. That x will give you this. That will give you your pH. When you put it in the pH formula, and we'll talk about that, look at this. You'll have 3 exponent 4 minus times 0.1 is equal to x squared. And then you do the square root of this. I'm getting a hydrogen ion or hydronium ion concentration of 5.477 times 10 to the minus 3. So let's put it down. Here x is equal to this hydrogen ion concentration, which is 5.477 times 10 to the minus 3 molars. What's the formula for pH? pH is equal to negative log of hydrogen ion concentration. All I'm doing is the log of this and a negative number. Why is n negative? Why is this going to be a negative? Because this is a fractional value. If you open it up, you're really looking at here 0.005477. When you do a log of this, you get a negative value. Hence, that equation has a negative to counteract the negative log you're getting. I have this value right here. I'm going to do its log and I'm going to hit this with a negative. My pH here is 2.26. At a system here where you have no base, you have a pH here of 2.26 and it will be right. Because now the pH is dependent solely only on this, because that's the only thing present here, because no base has been added. So this part has been done. Remember, everything always goes in this format after an equation has been developed. For these small Ka values, you can eliminate this item, because if you don't, you'll have a quadratic equation which will develop. You'll have to use a quadratic formula, but this assumption is very acceptable and it's encouraged. Now let's look at everything here with regards to the change in the pH. When you have 12.5 ml of base being added, now you know obviously the pH will go up, and we'll talk about it. Before we put the equation, let's talk about our equivalence point over here, because it will come in soon. The moles acid should equal to moles of base. What are my moles of acid? I'll just take this and that. I'll multiply in 0.1, and the molarity always has the units in terms of liters. That'll be 0.05 liters. Should equal to your 0.2 molar times a certain volume. This volume here will give you how much in terms of liters you can have base before that equivalence point is reached. You'll have 0.1, which is 0.1 molar of the weak acid, times 50 ml, which is really 0.05 liters, divided by 0.2. You're getting here 0.025 liters multiplied by 1000, and you get 25 ml. I'm having here 0.025 liters or 25 ml. I know here when I reach this point, I have my equivalence point right over there at 25 ml, so we have to keep that in mind. And we will. But we're not there yet, because we're going to look at 12.5 ml, and let's do that. Remember, this equivalence point calculation could have been done at the very beginning, but at some point you should do it. Your equation will become this now that you're adding base. You're adding sodium hydroxide, but you can just write that as this, OH minus you'll have this converted into conjugate base, and then you'll generate water. It'll pluck out the hydrogen from here and it'll attach and form water, and you'll have the conjugate base. Of course, everything will be start, change, and finish. But what will you put here? You can put here now the moles. You don't have to talk about molarities anymore, because now we have the combining in here of the base. What is our moles acid? It's 50 ml or 0.05 liters times that. It's 0.005 moles. And you can do that. Just do 50 ml divided by 1000, convert into liters, multiply by the molarity. Moles is equal to molarity times volume, which is this, 0.005. You can do exactly this for mole determination. You have your volume, you have your molarity. Let's do it. You have 12.5 milliliters divided by 1000 times 0.2 molar sodium hydroxide. You have 0.0025. 0.0025. We're in that part now of that titration curve where you still have less of this, more of this. So you can easily counteract any pH changes to a certain degree. You have zero amount of this. This is not included. You'll have this decrease by a certain amount, but that certain amount is known. It will be the exact amount of your base, because this base will neutralize to its fullest extent the amount it can neutralize from here. So you'll minus from it 0.0025. This obviously will go away as it's neutralized, and it will add up over here. What you'll end up seeing here is the final amount of your conjugate base is 0.0025. The base is fully neutralized when it hits this, it's 0, and this thing is halved. 0.005 minus that is 0.0025. Now what equation do we use over here? When you have a system here with a weak acid, weak base, you'll use this equation. pH is equal to pKa plus log base, conjugate base, divided by the acid. We have our equation over here, which will give us our pH of this entire system with 12.5 ml. Now let me give you your shortcut number 2. Shortcut number 2, you see how everything here is in moles, right? We've converted everything into moles, but here you're looking at molarity. Keep them in this. It wouldn't matter. When you're doing like item divided by like item, whether it was converted to molarity or whether you kept it into moles, it would make no difference. Just keep these into moles and your procedure will be simplified. How do we determine pKa? pKa is equal to negative log Ka. We have our Ka right over here. Let's figure it out. I have 3 exponent 4 minus, I'm going to do log on it, and I do negative. I get 3.522. That's my pKa. 3.522. I have coming here 3.522, and it will add to it the amount coming from here. What will be that amount? Well, look at it. You'll have the same item divided by the same item. Numerically, it will be log of 1. Log of 1 is always 0. 0.0025 divided by 0.0025. You log it. You get a 0. 0 adds to this. Your pH of this system is going to be 3.522, and your answer will be right. And I'm going to put it right over here. 3.52. Let's just keep it to that. You see how initially at 0 ml base we had a pH of 2.26. Now we've raised it up, but not a lot, because this weak acid can act as a buffer up to a certain degree, up to that point where the equivalence point is reached. Then the pH will shoot up, and then afterwards the pH is dependent solely on the amount of the base, because by then all the weak acid is neutralized and it's used up, it's consumed. So this part has been done. Notice how this equation came into the picture, because now you have a base in the system. Notice pK is equal to negative log Ka. Notice how I didn't convert anything here into molarities. I kept everything here into moles, because it wouldn't matter. There will come a point where you will have to do that conversion back into molarity, and that point is not too far away. Now let's look at the next part here with 25 ml of base in the system. Now we have 25 ml of base. We still have to put our moles over here. The equation is still the same, because you still have acid being hit by base. What's over here? We have 0.005 liters times molarity. What's over here? Molarity times your liters. Convert this into liters. 25 ml is 0.025. 0.025 times molarity 0.2, I'm getting 0.005. Now look, I'm seeing the exact amount of base in terms of moles as acid, which is my equivalence point. Here you're starting out with 0. You're going to start neutralizing everything here now by means of the acid is going to get used up. And here you'll get 0.005. Look what will happen. You'll have 0.005. Here you'll have 0. Here you'll have 0. What can we do now? We're kind of caught in the middle of a mess here. All we have is conjugate base. All of this is fully used up. And now is a point where things flip around in terms of your reaction, because all you have now is conjugate base, which will now begin to react with water on that side, and the reverse reaction will start happening. The reverse. What will happen over here is a reverse reaction, and now what you can do is start feeding in this into your next start, change and finish, which will then give you your pH calculation. A very interesting part right here is this fact that the reverse reaction will come in here because the weak acid is now beginning to fully get consumed because the equivalence point is reached. This right here is moles. Convert this now at this step into molarity. What's your volume? Volume is not this. Volume is the total volume of your system, which is here 50 ml of the weak acid and 25 ml. Your volume here is 75 ml. Convert this 75 ml into liters. Your molarity is equal to moles divided by that volume. Moles, 0.005 moles of that conjugate base divided by 75 ml, which is 0.075 liters. You get 0.06666 molarity, or molars. 0.06666 molar of conjugate base. That's what's coming here, 0.06666. You have now 0 of this because all of it got used up. See, 0, 0. This will start decreasing now. As the reverse reaction is going, this will start decreasing and these will start increasing. They'll increase to a certain amount, an X amount. This will decrease to a certain amount, 0.06666 minus X. Now will come our third shortcut, but think about it. Now we have a system here primarily based on a conjugate base. You have to now determine the base dissociation constant. You know that Kw is equal to Ka, Kb. If you were to multiply this with this, you should have that. If you want to find Kb, just do Kw, which is your 1 exponent 14 minus divided by your Ka. And that's exactly what you're going to do. 1 exponent 14 minus, which is the water dissociation constant, divided by the acid dissociation constant, 3 exponent 4 minus. You get here 3.333 times 10 to the minus 11. That's your base dissociation constant, 3.333 times 10 to the minus 11. That will come into this equation because now you're looking at the Kb equation. Kb is equal to this times this, x times x, which is just x squared divided by this. Your shortcut number 3, remove this x because your dissociation constant is so small that minus x is meaningless. You don't want to end up in a quadratic formula situation. It will be messy. You'll have just 0.06666 is equal to your base dissociation constant, 3.333 times 10 to minus 11. Here you'll solve for x, but here the x will equal to this, your base concentration, and you'll find that out. Base dissociation constant multiplied by 0.06666. We'll square root it because now we're doing x squared, we're square rooting it. I'm getting 1.4907 times 10 to the minus 6. Let's put it down. 1.491 times 10 to the minus 6. If I want to find the pH, I'm going to find the pOH. pOH is equal to negative log OH concentration. Let's do that. What's pOH? You're going to do the log of this and negative log and minus. I'm getting a 5.8266. My pOH. pOH is equal to 5.8266. Remember, logs of all of these fractional decimal values between 0 and 1 are always negative. Hence, the formula has a negative to negate that negative. Remember, the sum of your pH and pOH can be 14. If you do this and you subtract it from 14, you get your pH. You'll add it to 14, you get 8.17. Remember this very important formula, pH plus pOH is equal to 14. You know this. If I know this, I want to find this, I just take this on the other side and I minus it, and that's what I did. I get here 8.17. My pH of this buffer system at equivalence point is now 8.17. There's a dramatic shoot up of the pH because now the weak acid is entirely neutralized. The hardest part of these titration questions is what you do at the equivalence point. The easiest part of these titration questions is what happens initially and what happens at the end. Because initially you only have acid in the system, it's dominating. At the very end, acid is all used up, only the base is really present in the system and it's dominating. The equivalence point, you have an interplay between the both. That's why it's hard, but you see everything has come down here by means of an initial reaction and then the reverse reaction by means of conversion of Ka to Kb, by means of evaluation of pOH, then to determine pH by this formula right here. What remains now for the conclusion is to determine what happens at 37.5 ml, and then we will be done with this video. At 37.5 we're close. What's our system? There's an original acid, there's an original base, and you're having a conjugate base, and you're having water. An acid and base are being neutralized to generate water, and that. You have an initial start, you have a change, you have a final. What do we put here? What do we put here? In all instances, we can stay here with regards to moles. We always have 50 ml of 0.1, that's 0.005. Remember, you have excess amount of base. You have 37.5 and you have 0.2 molar. Convert that 37.5 ml into liters. You have 37.5 divided by 1000, that's liters, multiplied by the molar 0.2. Remember, moles is equal to molarity times volume. I get 0.0075. 0.0075. Here I have zero amount of this. How much are we going to decrease and how much are we going to add? Since this is in a deficiency, that's in an excess, your entire acid will get consumed and it will take away from the amount of your base, but it will add in the form of your conjugate base. What will you get over here? This will be 0. This right here will be a certain value. We'll do that. Minus 0.005. I'll get 0.0025 moles of this. This right here is negligible because in comparison between a strong base and a weak base, which is a conjugate base, this will always triumph and it will dominate in terms of the pH determination. You don't even have to look at this anymore. Everything will be based on this. We have to now determine this in terms of its molarity. That molarity is really your hydroxide ion concentration. Molarity is equal to moles over volume. We have the moles, it's 0.0025. We have the volume, but it's the total volume of the system. This plus that. 87.5 ml or 0.0875 liters. When you do this computation, you get your molarity with regards to the hydroxide, which is the base. You'll do 0.0025 divided by 0.0875, you're getting 0.02857. That's the hydroxide ion concentration. 0.02857. You're doing now a pOH calculation because there's no hydrogen ion concentration. It's all being used up, it's neutralized. You're doing a negative log of this value right here, which is your hydroxide, 0.02857. That'll give you your pOH value. You'll do the log of this. You get 1.544. 1.544, but that's pOH. pH is equal to 14 minus pOH, which is 14 minus 1.544. I'll take this value, I'll negate it, and I'll add it to 14. I get 12.455. 12.455, and that'll be my answer here. 12.45. Let's just do 12.45. Look at the pH changes. Initially, you only have acid, it's 2.26. You slowly start adding base, the pH starts rising, but not a lot because a buffer is at play. The buffer gets consumed up and used up at this equivalence point, the pH shoots up. After that, only the hydroxide ion is dominating and the pH is going to start shooting up closer and closer to 14 as you keep adding more and more sodium hydroxide. That right there will bring us to the end of this video. Remember how everything has come along in this video. Ka, Kb, the smaller these numbers, you can take those assumptions I showed you and eliminate the quadratic factors and keep everything easy. Remember how the equations have been with regards to how the system has changed with the addition of the base. This type of question is something which is not too hard when you look at it in a broken down manner as I've shown it to you over here. Thank you for watching. Have a good day.